Histidine is one of the 20 amino acids that's used to make a protein in the human body. Just like every other amino acid, histidine is going to have a central carbon, an alpha carbon, a chiral carbon, the carbon that has 4 different constituents or 4 different attachments to it. One of those attachments being a carboxylic acid. We have carbon, 2 oxygens, and a hydrogen. It's also going to have an amine group. We have a nitrogen with 3 hydrogens attached to it. Nitrogen should only ever have 3 attachments, and so because this has 1, 2, 3, 4 bonds on it, this nitrogen is going to carry a +1 charge. One of these should just be a lone pair on nitrogen. So this is going to carry a +1. It's going to have just a hydrogen attached to the central or the chiral carbon, and then it's going to have an R group. And in the case of histidine, this R group has 2 nitrogens in a ring. One of these nitrogens is good because it has the 1, 2, 3 attachments and then this lone pair. But one of these nitrogens is not good because it also has 4 bonds. You've got a double bond to this carbon, a hydrogen out here, and then also another bond to this other carbon here. So this is also going to carry a +1 charge. So you've got a +1 here and a +1 here. Overall, this molecule is going to carry a +2 charge. Now, as you increase the pH or lose the amount of hydrogen that's in the environment, and this molecule is going to start to have more hydrogens on it than the environment does, this molecule is going to start to give its hydrogens to the rest of the environment to help out the environment. The first hydrogen that's always lost from an amino acid comes from this carboxylic acid group. So you're going to go COO-. And now this oxygen has an extra pair of electrons attached to it. And so this carboxylic acid is going to carry a charge of -1. Nothing happened to this nitrogen, so it's still going to carry its +1. And nothing happened to this nitrogen, so it's also going to still carry its +1. So we've got +1, +2, -1. Overall, this molecule is going to have a +1 charge. And that's going to happen at about a pH of 1.8. Then if you keep going, decrease the amount of hydrogen that's in the system, which means there's going to be more hydrogens on this molecule. Now one of these nitrogens is going to end up losing one of its hydrogens. The first nitrogen that's going to lose a hydrogen is the one within this ring. This ring is very unstable because this nitrogen is not happy how it is, more so than this. It's kind of like, I don't like it. But this is like, this whole ring is unstable because this nitrogen's got an extra attachment. So it's going to lose its hydrogen. And by losing that hydrogen, it's also going to gain back its extra lone pair of electrons. So now this nitrogen is 0. So now we've got a -1 off of this. We've got a 0 here, and we got a +1 here. So now this molecule is going to be considered a 0 charge. And this happens at about a pH of 6.5. If you keep going up, losing the hydrogen that's in the environment, having more hydrogens on this molecule, the last part of this molecule that's going to lose the hydrogen comes from this nitrogen down here that's attached to this central carbon. And that's going to happen at a pH of about 9.3. It's going to gain back its lone pair. So now this one's 0, this one's 0, this is 0, and this is -1. Overall, this molecule is going to have a charge of -1. But that's only at pHs way above 9.3. At 6.5, it's going to start losing electrons from this nitrogen here. But it's not going to have fully lost on every single molecule that you see until at least a pH of 7.5. There's a little window of time. So at 6.5, it's going to start losing, but it's not going to stop losing until about 7.5. So the human body, some of the histidines are going to look like this, and some of the histidines are going to look like this, where this nitrogen is still carrying this +1 charge. So because we don't know exactly which histidines are going to have the nitrogen with the +1 and which of the nitrogens are going to be 0, we're going to assume that at least one of them is still +1 here, carrying this extra hydrogen. And so at physiologic pH, we assume histidine carries a charge of +1. You got this -1 here, you've got this +1 here, that balances out to 0, and then you've got this extra +1 here. So overall, this molecule is going to carry a +1 charge. Now let's talk about the R group. So the R group of histidine, you've got a carbon with 2 hydrogens attached to it, and then a ring where you've got 2 nitrogens in the ring, 3 carbons in the ring, and a whole lot of hydrogens. Nitrogen is one of the most electronegative elements on the periodic table. So all of these bonds, this nitrogen to this hydrogen, as well as this nitrogen to this carbon, all of those bonds are going to be polar bonds. If you look overall at this molecule, there are more polar bonds than non-polar bonds on this molecule because of these nitrogens. So this molecule overall is considered polar. And because it's polar, these lone pairs, as well as these polar bonds, are all spaces where hydrogen bonding can occur. And as long as a molecule can do hydrogen bonding, it's able to bind to water, which means that it likes water or is hydrophilic. So this R group, the R group for histidine, is both polar and hydrophilic. However, because this nitrogen is carrying an actual formal charge of +1, it's going to be basic. So yes, it is polar because of all those nitrogens, but more importantly than that, it's going to be basic because it actually has a +1 charge on this R group. This ring where you've got these 2 nitrogens, the 3 carbons, this is called an imidazole ring. So if you ever see something where you've got the 2 nitrogens, 3 carbons, all these hydrogens attached to it in a ring form where these nitrogen has 1 double bond, and then there's a carbon to carbon double bond as well, this is always called an imidazole ring. This ring is way too complex for your human body to make. So the amino acid histidine is going to be essential. You have to be able to eat it in order for it to show up in your human body. You're not able to make it in the body itself. But this ring is going to be showing up in a whole lot of other molecules, including histamine. So this imidazole ring, although you got to eat it, your body recycles it in so many other places that it's used to make other molecules.